Bismillahirrahmanirrahim. Inshallah, we're going to continue with our chapter 4. According to the text, this is chapter 18, entitled as temperature. So, if you look at this picture, on a very hot day, the bricks on the sidewalk, has buckled. Okay, what happened here? Okay, when the temperature increases, it means that lots of energy going to be received by the bricks, whereby the bricks going to expand, and if there is no space for the bricks to expand, this what going to happen, which is the brick going to be buckled. All right. So up to this point, we have focused on mechanical situation in previous topics, which generally involve macroscopic objects. For example, we've looked at kinetic energy of cars, billiard balls, planets, and rolling wheels. We perform calculation using potential energy in system of springs, a ball and the earth, a planet and the sun. In this chapter, we begin to investigate thermal phenomena, where we introduce internal energy in chapter 7, where we talk about something becoming warmer due to friction. That was our first hint of the thermal process. The hallmark of the thermal processes is that they involve energy on the microscopic scale, which is in atomic level, right? As we shall see in chapter 20 coming, we can relate the temperature of an object to the kinetic energy of the molecules of the object. We introduce the energy transfer process of heat in chapter 8 as a means of transferring energy into or out of system, if you still remember. And in chapter 19 later, we will discuss this process in terms of microscopic collision between molecules at the boundary of the system. To establish the basis of this discussion in the next chapters, we will firstly embark in this chapter on macroscopic understanding of the concept of the temperature and its effects. This chapter concludes with a study of ideal gases, on the macroscopic scale. In this study, we connect the quantity of the pressure from chapter 14 to that of temperature from this chapter. Once we understand the thermal phenomena, we will see, for example, thermal effect of the electrical resistance in chapter 26, on magnetic properties of material in chapter 29, on radiation from a hot surface in chapter 39, and so on. So means this is like a very base, for the coming topics. Right. So 18.1, temperature and zeroth law of thermodynamics. So what is temperature? Temperature is actually an indicator of hotness or coldness of an object. So if let's say we touch a tile, or we touch a bricks, or we touch a metal, we will feel the metal is cooled. From one person to another person, how cold an object is or how hot an object is may vary, because we have a different sensing, right, of level of sensitivity. Right, so we need a standard, a reliable, unit to measure hotness and coldness. So we need a temperature scale, to be referred to. Right, so look at this. This is, we have an object A and an object B. Let's say we would like to know what is the temperature of object A. We are going to use our thermometer, symbolized as object C. So when we touch or measure the temperature of object A, we come out with this reading. And now, happen to be, we want to measure the object B, the temperature of it. So again, we're going to repeat the measurement by using our thermometer system, symbolized as C. If, let's say, the reading of the temperature for object B is the same to the reading of the temperature for object A, we may conclude that it seems like, object A and object B is in thermal equilibrium. Right. First thing first, object A and object C does the thermal contact. What does that mean by thermal contact? There is a contact between two objects where the temperature of the two objects is different. So thermal contact happen here. After the thermal contact, whenever we want to get the reading, the two objects, A and C here, have to reach thermal equilibrium firstly. Where thermal equilibrium is a situation which two objects would not exchange energy by heat or electromagnetic radiation if they were placed in thermal contact. That is why the moment we touch object A, we cannot directly take the reading. The reading going to fluctuate firstly. So we have to allow some duration or period, and then finally object C, the thermometer, going to give us final reading. The final reading means there is no more exchange of heat between object A and object C. So we get this reading. Goes the same to object B and C. And finally we get this reading. If the reading of this temperature is the same to this temperature, it means that A seems like having a thermal contact and reaching thermal equilibrium with B. Even though in a physical or real case that A does not in contact with B. But since the reading is the same, it seems like we can conclude that A also in thermal contact and thermal equilibrium with B. Thermal equilibrium means that no energy will be exchanged between A and B when they are placed in thermal contact with each other. What does that mean by thermal contact? Whenever two objects touching each other and has different temperature. Right? So this is actually the zeroth law of thermodynamics. If object A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. So this is the zeroth law of thermodynamics. So quick quiz 18.1. Two objects with different sizes, masses and temperatures are placed in thermal contact. In which direction does the energy travel? Option A. Energy travels from the larger object to the smaller object. B. Energy travels from the object with more mass to the one with less mass. C. Energy travels from the object at higher temperature to the object at lower temperature. So, which one is the correct answer? Right? The correct answer is C, where the energy travels from the object at higher temperature to the object at lower temperature. Right? We also name this as temperature gradient. This is the Sunnatullah, where for two objects is in thermal contact and the two objects has different temperature, the heat or energy going to flow or travels from object at higher temperature to the lower temperature. This process going to be stopped whenever the T final of object 1 and object 2 is the same. Okay, it means that no more energy or heat going to be transferred between the two objects. It means that the two objects reach thermal equilibrium. So, talking about temperature just now is a measure of the hotness and coldness. Okay, we need the device to measure the temperature. The device known as thermometers. Okay, and we need the scales to read the temperature. Okay, where here we have few types of scale. The first one we're going to take a look on the Celsius temperature scales. Okay, so this is mercury. Okay, mercury thermometer that is commonly used in our laboratory. Okay, the level of mercury in the thermometer will rises, okay, as the mercury is heated by water in the test tube, right? Initially, the temperature of the mercury is at room temperature, let's say 20 degrees Celsius. And then we are going to immerse the thermometer, the mercury thermometer, into hot water, right? So what will happen? The final reading of the mercury, okay, is 30 degrees Celsius. So it means that, okay, there is a change in temperature by 10 degree. Okay, so due to what? Due to the energy transfer from hot water to the cold object, which is our thermometer, due to the temperature gradient. We have to have the reference point. Okay, our basic reference point is 0 degrees Celsius and 100 degrees Celsius. 0 degrees Celsius is ice point of water, and 100 degrees Celsius is steam point of water. So this is as the standard. So to calibrate a thermometer, we're going to use a mixture of, okay, water and ice, which is at 0 degrees Celsius, and then we are going to place our thermometer into the mixture of the ice and water. And then after that, we are going to immerse, okay, the thermometer into steam, combination of steam and water. Okay, steam and water at 100 degrees Celsius. Okay, and then we are going to divide the scale into 100 points. Okay, 100 divisions. So means that from 0 to 100 degrees Celsius, we are going to have 100 divisions. For one division, it represents 1 degree Celsius. That is how we define scale for the Celsius. We also may use other than mercury to replace the mercury with the alcohol, with any other kind of liquid. Okay, but then there is a limitation where the temperature, the maximum temperature can be measured by certain liquids must be below its boiling point, okay, or vaporization point, right? Now the constant volume gas thermometer, right? One version of the gas thermometer is the constant volume apparatus shown in figure here. This is figure 18.3 from page 485. Okay. The physical change exploited in this device is the variation of pressure at a fixed volume of gas. Okay, here. Okay, with temperature. Right. The flask here is immersed in an ice water bath. And mercury reservoir, this is mercury reservoir. Okay, we have reservoir A, we have reservoir B. Right. The mercury reservoir B is raised and lowered. This will cause mercury to transfer between reservoir A and B through the flexible hose here. Okay, reservoir B, okay, is adjusted until the top of the mercury in column A is at 0 scale. Okay, the height h, okay, the difference between the mercury level in the reservoir B and A, which is the H here, right, indicates the pressure in the flask at 0 degree Celsius by means of equation P equivalent to P naught plus rho GH, where P naught, okay, is the atmospheric pressure. This is absolute pressure, and this one is gauge pressure. Gauge mean the device, the one we measure just now. This is atmospheric pressure, which is equivalent to ATM, and this one is absolute pressure. Okay, and then next one we are going to repeat, okay, the same method where now the flask, okay, is then immersed in water at the steam point, right. Receiver B is again readjusted until the top of the mercury on within column A at the 0 level of the scale, right, which ensures that the gas volume is the same as it was when the flask in the ice bath just now. Okay, so with this we are designing constant volume system. This adjustment of receiver B, okay, give a value of the gas pressure at 100 degrees Celsius. Okay, these two pressure and temperature values are then plotted as shown in this graph. We have at 0 degrees Celsius, what is the reading of our pressure, right? And then whenever we immerse the flask of the gas within steam water system, then we are going to have the reading of new pressure here. So by plotting these 2 points and the 2 dots here represent known reference temperature, the ice and steam points of water, right. This is how we measure the pressure and temperature of a gas. Okay, the line connecting between the 2 points serve as the calibration curve for unknown temperature. Okay, other experiment shows that linear relationship between pressure and temperature is a good assumption. Okay, to measure the temperature of a substance, the gas flask on figure 18.3 is placed in thermal contact with the substance, and the height of the receiver B is adjusted again until the top of the mercury in column A is at 0 scale. Okay, the height of the mercury in column B indicates the pressure of the gas. This is the method to measure pressure within a gas. Okay, now suppose temperatures of different gases at different initial pressure are measured with a gas thermometer. Okay, the output of it will be 3 line here. Okay, so if we have extrapolate the data, okay, we will see they are going to meet at one point, which is negative 273.15 degrees Celsius. Okay, for this point, okay, we call it as absolute zero. Okay, so this means that pressure will be totally zero at this degree. Okay, so means that all of the gas almost not moving at all, because the movement of the gas producing pressure, right? So this is also known as temperature scale, which set negative 273.15 degrees Celsius as 0 point, or we call it absolute zero. Okay, and for temperature in Celsius is equivalent to T minus 273.15, which is TC here is temperature in Celsius. The absolute zero here, okay, does not depend on the atmospheric pressure or any particular material. Okay, the second reference temperature of this new scale was chosen as triple point of water, which is the single combination of temperature and pressure at which liquid water, gaseous water, and ice, which is solid water, coexist in equilibrium, which is this is at 0.0 degree Celsius and pressure of 4.58 millimeter of mercury. The triple point of water is the same everywhere. On the new scale, which uses the unit Kelvin, the temperature of water at the triple point was set at 273.16 Kelvin, abbreviated as 273.16 or 15 Kelvin. Okay, so we have Celsius, Fahrenheit, and Kelvin temperature scales. So it serves the same purpose, but then with different approach. So here is in Celsius. If you want to put it normally in USA, they use it in Fahrenheit. This is on how to convert, right? This is 0 degrees Celsius, okay, equivalent to 32 degree Fahrenheit. So this is a conversion equation. So delta T of temperature in Celsius is the same to delta T in Kelvin, is equivalent to 5/9 delta T in Fahrenheit. Or you may use your calculator to convert it directly. Example 18.1, converting temperatures. On a day when the temperature reaches 50 Fahrenheit, what is the temperature in degrees Celsius and in Kelvin? So by applying the equation in previous slide, okay, we may directly determine this, okay, which is in degrees Celsius for 50 Fahrenheit is actually 10 degrees Celsius. Okay, in a Kelvin scale, right, is actually 283 Kelvin. The SI unit for temperature is actually Kelvin. Okay. Now, thermal expansion of solid and liquids. Our discussion of the liquid thermometer actually make use one of the best known thermal changes in a substance. As its temperature increases, its volume increases. Okay, this phenomenon known as thermal expansion actually. It plays an important role in numerous engineering applications. Okay, we can use lots of it. Okay, for example, thermal expansion joint, as those shown in this figure, right? And also in this figure. Okay, we must include this pattern or method or space, okay, in the building, concrete highways, railroad, okay, tracks, bricks wall, bridge, to compensate for the dimensional changes that occur as the temperature changes. Right. Thermal expansion is the one that responsible for this effect, okay, of seems like buckle system. Thermal expansion is consequent of the change in the average separation between the atoms in an object. Okay, to understand this concept, let's model the atom as being connected by a stiff springs as discussed in section 15.3. Right, like this. So if let's say this is one atom connected to the neighboring atom, and so on by a light spring. Okay, when you supply heat to the system, you are going to supply heat, okay, which is Q, okay, to the system, add up, right? What will happen? All of the system or all of the atom going to vibrate more. Okay, it's going to vibrate more than its normal temperature. This is 3D, okay? Up and down, left, right. Okay, consequence of it, what will happen is, okay, goes the same here. Right, consequence of it, as a whole, okay, the vibration here going to make the distance between this to this bigger in comparison to the initial distance. This is for one molecule, okay, for one material, let's say one bricks, okay, consists of lots of, okay, molecules, right? So as a whole, we are going to observe that it's going to slightly elongate. Okay, so slightly elongate, we call it thermal expansion. So there is 3 types of thermal expansion of solids. The first one is linear expansion. For linear expansion, involve one dimension. Okay, for example, change in length. Okay, due to the heat transfer into the system the atoms going to vibrate more. So as a whole, consequence of it, okay, the material going to elongate. Okay, for this example, this railroad, okay, the elongation going to cause the system to be shifted like this, right? So how much the change in length of the system ratio to the initial length of the system must equivalent to or directly proportional to the alpha. Here is the linear coefficient of thermal expansion. Actually, okay, the relationship is like this. How much changes happen ratio to the original length is directly proportional to the temperature, change in temperature experienced by the system. If we want to convert it into mathematical expression, then we are going to have delta L over L initial equivalent to a constant times delta T. This constant is alpha. This alpha is known as linear coefficient of thermal expansion. Alright, and the alpha going to be in unit either per degree Celsius or per Kelvin, depending on the unit of your delta T. Right. So it could be your delta T could be in Celsius or could be in Kelvin, vice versa to this. It must cancel out each other so that the final unit is about here only. Right. So we may rearrange this equation into this. Within delta L is L final minus L initial. Within delta T is T final minus T initial. Or we may rearrange it to this method. Right. Second type of thermal expansion of solid is area expansion. So if let's say you have a ring metal material like this, okay, this is the original radius, inner radius of it, outer radius of it. When you supply heat to the system, we know that this system going to expand slightly. So we have addition of delta A, okay, and addition of delta B due to the delta T supplied to the system, right? We may have the delta A of the whole system because it's expanding in terms of area, where it involves two dimension, right? When it involves two dimension, then we have delta A. Delta A is equivalent to A minus A original or initial, equivalent to gamma A naught delta T, right? Where gamma here is twice of alpha because it's two dimensions, okay? Alpha only one dimension. For gamma, it's two dimensions, so it's twice of alpha. So it's actually coming from the same method, delta A, okay, over A naught or A initial is directly proportional to the delta T. When we convert it into mathematical expression, it's equivalent to alpha gamma is equivalent to gamma delta T, okay, where gamma is twice of alpha, right? The third type of solid thermal expansion in solid is volume expansion, okay, where we have here, okay, let's say changes happen in 3 dimension. It's 3 dimension. Expansion happen in 3 dimension. So if this is the case, okay, by using or applying the same method, delta V over V initial or original is directly proportional to the delta T supplied to the system. Therefore, delta V over V initial or original equivalent to a constant, which is beta delta T, right? And the beta here is the coefficient of volume expansion, equivalent to 3 times alpha because it's expand in terms of 3 dimensions. So table 18.1 listed here variation values of average linear expansion coefficient, which is alpha. If you see here, the unit is per degree Celsius. Okay, for different material has different value. So to our naked eyes, it's almost nothing, isn't it? Because it's order of -6. Okay, but then actually this material has the elasticity properties because it can expand and back to its original size. Okay, for liquid and gases, okay, normally liquid and gases going to expand in terms of volume. That is why given here is beta. Okay, so also the same, right? But which is bigger compared to solid. That is why to our naked eyes, it seems like bricks or wall or concrete or road or metal seems like does not expand to us by our naked eyes. But actually it does expand, but the scale is very small in amount. Example 18.2, expansion of the railroad track. A segment of steel railroad track has a length of 30 meter when the temperature is 0.0 degrees Celsius. This one. A. What is its length when the temperature is 40 degrees Celsius? So by using, we know this is about length only, one dimension. So we are going to use the linear expansion. Delta L equivalent to alpha L initial or original delta T. So alpha here, if you refer to the table just now, okay, for the steel, okay, it's 11 times 10 to the power of -6 per degree Celsius times the L original is 30 times the delta T must be in Celsius as well, because the unit of this and the unit of this must cancel out. Okay, then finally we're going to have the unit of this is in meter, representing the delta L. But the question asking for, okay, what is its length when the temperature is 40 degrees Celsius? It means that this is L final. So L final must be L initial, because in delta L is L final minus L initial. So if you want to have L final, must be delta L plus L initial. So this is what are we doing here. Okay, what if the temperature drops to negative 40 degree? So in opposite, okay, what is the length of the unclamped segment? So it's going to be, okay, 30 minus 0.013. Easy, right? You may repeat this calculation all over again as well by using delta L. By using delta L equivalent to alpha L initial delta T. You're going to prove that again. Okay, you will get the same delta L. You're going to see that, okay, your delta L will be in negative amount because it's not expanding but compressing or contract. Okay, so then you're going to have your L final equivalent to 22.987 meters. You may try this method, okay? Okay, now example 18.3, the thermoelectrical shock. Okay, a poorly designed electronic device has two bolts attached to different parts of the device that almost touch each other in its interior as in the figure. This one. Okay. The steel and the brass bolts are at different electric potential. And if they touch, a short circuit will develop, damaging the device. We will study the electric potential in chapter 25. Okay. The initial gap between the ends of the bolts is D equivalent to 5 millimeter at 27 degrees Celsius. At what temperature will the bolts touch? Okay, assume the distance between the walls of the device is not affected by the temperature. This one and this one, okay, is not affected. Okay, so what are we going to do? We are going to sum the delta of the brass plus delta of the steel, okay, mass equivalent to the D. Then it's going to be in touch with each other. So, okay, the delta L of the brass is defined by this. This one is this. And this one is this. Right? So, rearrange the equation because we want to know the temperature. Okay? At what temperature? Okay? So, that this is going to happen. Right? So, the D divided by this. Right? Then you will get delta T is equivalent to 7.4 degrees Celsius. Okay. So, the T final. This is actually not the T. This is the T final where, okay, from 27 degree must be increased to 7.4, which is equivalent to 34 degrees Celsius. Okay, then this is going to happen, whereby this one going to expand, this one going to expand, then they're going to touch each other. That is why the total of the expansion between the brass and the steel equivalent to the separation distance.